Somewhere out past the edge of everything the sun protects, one of two identical spacecraft did something its own twin, launched from the same site 16 days apart, carrying nearly identical instruments, was never able to do. It didn't fly faster. It didn't travel farther. It simply had one working part its twin had lost decades earlier. And because of that single surviving instrument, it caught, in real time, the exact moment the solar wind around it dropped to nothing. Its twin could only infer that moment after the fact, piecing it together from indirect clues. The spacecraft watched it happen. That difference sounds small. It isn't. It's the reason we now have direct, measured proof of what the true edge of our solar system actually looks like from the inside. Proof that's forced scientists to revise their picture of that boundary more than once. Most recently in research published in 2024, suggesting the edge of the solar system isn't a line at all, but something closer to a thick, turbulent layer, unlike anything the earlier models predicted. And the story of how one spacecraft managed to see something its identical twin couldn't is not a footnote. It's one of the more remarkable pieces of engineering luck in the history of space exploration, and it's still shaping what we understand about the boundary between our solar system and the rest of the galaxy. This is Voyager 2, and this is what it saw that Voyager 1 never could. To understand why one working instrument mattered so much, you have to go back to how these two spacecraft came to exist in the first place. Voyager 1 and Voyager 2 launched from Kennedy Space Center in the late summer of 1977, Voyager 2 first on August 20th, and Voyager 1 second 16 days later on September 5th. Despite the numbering, Voyager 1 was put on a faster, more direct trajectory and overtook its sibling within about a year. Both were built for a 5-year mission with one clear goal: fly past Jupiter and Saturn, take pictures, gather data, then fade into retirement. Nobody on the design teams was planning for machines that would still be transmitting in 2026. Voyager 1 took the fast route through the Jupiter and Saturn system, and then aimed itself out of the plane of the planets entirely, using a close pass by Saturn's largest moon, Titan, to bend its trajectory sharply, trading any further flybys for a closer look at Titan's thick, hazy atmosphere. Voyager 2 took a slower, more patient path, and because of a rare alignment of the outer planets that happens only once every 175 years or so, mission planners realized they could send it onto Uranus and Neptune as well, something no other spacecraft before or since has attempted. Voyager 2 became the only spacecraft in history to visit all 4 giant planets up close. At Uranus, in January 1986, it discovered 10 previously unknown moons and 2 new rings, and found a planet tipped almost completely on its side, spinning like a rolling ball rather than a top. At Neptune, in August 1989, it found 5 new moons, 4 rings, and a vast rotating storm nicknamed the Great Dark Spot. It remains to this day the only spacecraft that has ever been to either planet. That single fact alone would have secured its place in the history of exploration. What happened after, once both spacecraft turned toward interstellar space, secured something more. Both probes eventually aimed for the same distant boundary, the heliopause, the point where the sun's outward stream of charged particles, the solar wind, finally loses its strength against the pressure of the interstellar medium pushing back from outside. Picture the solar system as sitting inside an enormous bubble the sun blows around itself simply by existing. The heliopause is the skin of that bubble. Cross it, and you're no longer in the sun's neighborhood. You're out in the space between stars, in a region filled with the debris of stars that finished burning long before humans existed. Voyager 1 got there first, crossing the heliopause in August 2012, 35 years after launch, at a distance of roughly 11 billion miles from the sun. It was a landmark moment, the first time anything built by human hands had left the solar system. But there was a complication. One that had nothing to do with distance and everything to do with a piece of hardware that had failed decades earlier. Voyager 1's plasma science experiment, the instrument specifically built to directly measure the speed, density, and temperature of the solar wind surrounding the spacecraft, had stopped working all the way back in 1980, not long after its Saturn flyby, likely due to a failed power supply component. So when Voyager 1 finally reached the heliopause in 2012, the single most direct tool for confirming that crossing had already been dead for 32 years. Scientists had to identify the moment using indirect evidence instead. A sudden jump in the density of galactic cosmic rays reaching the spacecraft. Subtle shifts picked up by the magnetometer. Secondary signals that, pieced together carefully, painted a convincing picture. It was enough. Researchers were confident in the conclusion, and the finding held up under peer review. But it wasn't the same as watching the solar wind itself simply stop. Voyager 2 reached the same kind of boundary 6 years later, in November 2018, at a completely different location on the far side of the solar system. And its plasma science experiment was still running. For the first time, mission scientists could watch the actual moment happen, rather than reconstruct it. On November 5th, 2018, That instrument recorded the speed of the solar wind particles around the spacecraft dropping sharply, and then, from that point onward, detecting no solar wind flow at all, not inferred, not pieced together after the fact from secondary clues, measured directly in real time as it happened. It's the difference between a detective reading a case file weeks after a crime and a witness watching it unfold in front of them. "This is what we've all been waiting for," said Suzanne Dodd, Voyager's project manager at NASA's Jet Propulsion Laboratory, in NASA's announcement of the crossing. "Now we're looking forward to what we'll be able to learn from having both probes outside the heliopause." That single working instrument turned Voyager 2 into something more than a second data point trailing behind its more famous twin. It became the calibration tool that let scientists finally trust what Voyager 1 had shown them years earlier, and, in a few important places, correct it. Here's where the story becomes genuinely strange, in a way that has nothing to do with speculation and everything to do with hard data neither spacecraft's original builders could have anticipated. Before Voyager 1 reached the heliopause, researchers expected the boundary's distance from the Sun to shift depending on where the Sun was in its roughly 11-year activity cycle, swelling outward during periods of high solar activity and contracting inward during quieter stretches, the way a lung expands and contracts with breath. Voyager 1 crossed during a period of high solar activity. Voyager 2 crossed 6 years later during a noticeably different point in that same cycle, and on the opposite side of the solar system entirely. If the breathing bubble model held up, the two crossings should have happened at meaningfully different distances from the Sun. They didn't. Both spacecraft found the heliopause at almost exactly the same distance, despite crossing at different phases of the solar cycle and from entirely different directions. "We don't understand why that is," said Stimatios Kremigis, a longtime instrument lead on the mission at the Johns Hopkins Applied Physics Laboratory, in a statement issued alongside the published findings. That's not a line inserted for dramatic effect. That's a career physicist on the record through NASA's own communications office, acknowledging that a basic prediction about the shape of our solar system's edge simply didn't hold up once it was actually measured twice. Voyager 2's working plasma instrument turned up something else as well, something its magnetometer then confirmed independently. Scientists had expected the magnetic field just outside the heliopause, out in true interstellar space, to point in a noticeably different direction from the magnetic field inside the bubble, since the two fields originate from entirely different sources, one from the Sun's rotation, one from the wider structure of the galaxy. Voyager 1's single magnetometer. Reading beyond the boundary had hinted that the two fields were oddly aligned, nearly parallel, but with only one data point, researchers couldn't be certain whether that was a genuine pattern or simply a coincidence tied to Voyager 1's particular location along the boundary. Voyager 2 gave them a second independent measurement from a completely different position on the far side of the solar system, and it confirmed the same alignment. Two magnetic fields from two entirely different sources, sitting in close agreement with each other at the edge of everything we call home. NASA's own science communications team described this directly, noting that the observation from Voyager 2 confirmed what had initially looked like a surprising, possibly coincidental result from Voyager 1. That finding still doesn't have a fully settled explanation, and it's part of what pushed researchers to reconsider what the boundary itself actually looks like. There's a third discovery that came specifically from Voyager 2's position. One Voyager 1 was simply never in a place to make. Voyager 2 crossed the heliopause closer to the flank of the heliosphere's bubble shape, rather than near the leading edge where Voyager 1 had crossed years earlier. From that different vantage point, one of Voyager 2's particle instruments picked up evidence, described in a statement from the Johns Hopkins Applied Physics Laboratory, that the heliosphere's outer boundary isn't a perfectly sealed wall after all. A trickle of particles from inside our solar system was detected slipping through the boundary into interstellar space, a slow leak in what scientists had once pictured as a clean, sealed barrier. If the heliosphere is a ship sailing through the galaxy, researchers noted, the hull turns out to be somewhat porous, at least along the flanks. Then, in early 2024, a new analysis combining years of data from both Voyager 1 and Voyager 2 suggested something that reshaped the picture even further. Rather than a thin, sharply defined boundary line separating our solar system from interstellar space, researchers proposed that the heliopause may actually be a thick transitional layer, a zone where the Sun's magnetic field and the galaxy's magnetic field interact and blend rather than meeting at a hard edge. That idea helped explain a puzzle that had bothered scientists ever since Voyager 1's original crossing back in 2012. Why the direction of the magnetic field measured by both spacecraft didn't shift the way a clean, thin boundary crossing should have produced. Instead of picturing a border like a line on a map, imagine something closer to a wide, turbulent coastline where two ocean currents mix gradually across a broad stretch of water rather than meeting at a single sharp edge. That remains a live, evolving area of research, And it exists specifically because two nearly identical spacecraft, launched 16 days apart, ended up crossing that region years apart from different directions, with different instruments still functioning at the critical moment. This connects to a broader debate that's been running quietly through heliophysics for years, largely because of exactly this kind of dual data set. What shape is the heliosphere actually in? For a long time, the working assumption, based partly on analogy with how other stars' astrospheres appeared to behave, was that our solar system's protective bubble trailed behind the sun's motion through the galaxy, the way a comet's tail trails behind its nucleus, long and drawn out. More recent modeling, built using data from both Voyager spacecraft alongside a NASA mission called IBEX, which studies the boundary from Earth orbit using particles that bounce back from it, has suggested the shape may be closer to a compact croissant, like curve, deflated rather than stretched. That disagreement hasn't been fully settled either, and it's a direct consequence of the fact that we currently have exactly 2 points of direct ground truth data from the boundary itself, collected years apart from different angles, by 2 machines with slightly different working instruments. Every model of the heliosphere's true shape has to be built around whatever those 2 data points can support, which is part of why researchers have been so protective of keeping both spacecraft alive as long as possible. None of this happened because engineers planned it that way from the start. Nobody sitting in a design review in 1976 decided that Voyager 2's plasma instrument should outlive Voyager 1's by more than 3 decades in order to eventually solve a heliopause mystery that didn't even have a name yet. It happened because of ordinary hardware variants, the kind of small manufacturing and operational differences that separate 2 nominally identical machines built side by side on the same production line. And it happened because Voyager 2 simply happened to still be capable of direct measurement at the exact moment it mattered most. Sometimes, the biggest scientific payoff isn't the result of a plan. It's the result of one piece of equipment quietly outlasting its twin by exactly long enough. That kind of accidental redundancy is rare in engineering, and it's part of why both spacecraft are still being operated with such deliberate, almost obsessive care today, even as their power supplies continue to fade year after year. Both Voyagers rely on radioisotope thermoelectric generators, sealed units that convert the heat produced by decaying plutonium into electricity. Both lose a small, steady amount of power every year, with no way to refuel or replace the source once it's gone. Voyager 2's plasma instrument, the one responsible for all of this, was finally shut down in October 2024. Not because it broke, but because the mission team could no longer justify the power it required, given everything else on the spacecraft that still needed electricity to keep functioning. It had operated for 47 years straight, more than 11 times longer than its original design life of 4, and it went dark, having already done something no other instrument on either spacecraft managed to do. Voyager 1 is now the more power-constrained of the 2, having already lost 7 of its original 10 instrument packages. Engineers are currently testing an experimental power recovery procedure on Voyager 2 first, precisely because Voyager 2 currently has a slightly larger remaining power margin to work with, making a failed test there less costly to the overall mission. If that test succeeds, the same fix will be attempted on Voyager 1 later this year. In a quiet sort of way, the roles have reversed from where the mission started. Voyager 2, once regarded as the slower secondary spacecraft on the less glamorous trajectory, has become the test bed responsible for keeping its more famous, faster-traveling twin alive a little longer. Both spacecraft are now expected to lose the last of their usable power sometime in the early 2030s, ending nearly 6 decades of continuous operation from 2 machines that were only ever designed to last 5 years. When that silence finally arrives, it won't come suddenly. It will be the last faint signal from an antenna that has been quietly reporting home since before most people alive today were born, arriving after a journey of many hours across a gap so wide that light itself, the fastest thing that exists, takes the better part of a day to cross it. Even after the signals stop, neither spacecraft comes to rest. There's nothing out in interstellar space to slow them down, no atmosphere, no meaningful friction, nothing strong enough to meaningfully pull either one off its course. Both are carrying identical copies of the Golden Record, the gold-plated copper disc holding greetings recorded in 55 languages, sounds of rain and ocean waves and human laughter, and 90 minutes of music selected to represent the breadth of human culture across history. The record was assembled by a committee led by Carl Sagan, built on the chance that someone, someday, somewhere far from here, finds one of these 2 machines drifting through the dark and wonders where it came from and who sent it. What Voyager 2 leaves behind, beyond the record, beyond the closer look at Uranus and Neptune that only it was ever positioned to provide, is something quieter, but just as important. Proof that even 2 nearly identical machines, built side by side, launched 16 days apart, can end up telling 2 different parts of the same story, simply because one of them happened to keep a single instrument alive long enough to witness something its twin could only guess at from a distance. It's a reminder that, in science, the biggest discovery isn't always about building something entirely new. Sometimes it's about one old machine holding on just long enough to see something for real, instead of everyone having to take someone else's word for it. Whatever Voyager 2 and Voyager 1 still have left to tell us about the true edge of our solar system, they're telling it right now, in real time, with the clock already running on how much longer either one of them will still be able to speak. If you want to see how far that story still goes, this is worth sticking around for. Subscribe if you'd like to follow it.